So next we have two short talks, two 15-minute talks, and then we can head up for lunch. The first one is by Dave Ditzel. He's the founder and CTO of Esperanto, previously VP of Intel, CTO of Sun Microsystems, and founder and CEO of Transmeta. So he will also give us an update on the Esperanto chip. Please, Dave.
Hey, thanks very much. I'm actually very excited today to talk about a subject I'm very passionate about, which is the merging of HPC and machine learning. And what I really believe is that RISC-V is absolutely the best foundation for both machine learning and HPC and building this into a single system here. If you look at how computing has changed for the last several years, machine learning has just absolutely taken over. And then with ChatGPT, just in recent weeks, the world has changed here, right? And that's really going to accelerate growth even more. HPC is doing well, a little bit more stable. You can track 40 years of growth and plot it, right? But I think my contention is it can't afford to be an isolated island. You can't build a giant HPC supercomputer and say, oh, well, it doesn't run ChatGPT. I can't do any machine learning. I have to buy another system that's almost identical to that. Well, that doesn't make any sense because the needs of HPC and machine learning are actually pretty similar. There's really no need to build two systems, one optimized exactly for each one of those tasks. Both of those tasks are really dominated by, there's a lot of compute and a lot of memory bandwidth. It's very fundamental to both, and of course, memory capacity, and there's many other issues. But a lot of these things are in common. And my view here is for the systems we want for the future, the big issue is how do we make these machines easier to program, right? I hope there's nobody in here who says, oh, I would really love to program in CUDA as a way to get there, right? Everybody knows that's very difficult here. Well, that's where RISC-V really has an opportunity here. So we think that RISC-V is in a very unique position to let us build the best, what we call a converged HPC and ML system. And we're hearing this from customers in the Department of Energy and others that go, well, why can't you guys build one machine that's good for both? So can RISC-V really take on both x86 and GPUs? And I'm here today to say absolutely yes, and to give you the evidence for that. Because we've been building real silicon. We have enough experience now to actually see where we're going and have a proof point here of what's going on. So our proof point starts with the chip that we have here today. We put over 1,000 full 64-bit RISC-V CPUs on a single piece of silicon. And the power is just incredibly low. From anybody else, you'd get maybe 32 CPUs for 700 watts. We do this for, I would say as low as 13 watts, but maybe up to 40 watts. It's very application dependent on what you're doing here. I won't go into all the details of the features here, but I want to give you a taste of what we've done. Because unlike a lot of the talks of people saying RISC-V is going to be great when it gets here someday, this is here now. You can have this now, and this will work and plug in and talk to other systems here. For example, I say in the Ventana talk, right? They kind of showed having an accelerator. Well, we could talk to that over a PCIe bus or other issues here and use our chips as an accelerator. So you could build a 100% RISC-V system here. So here's the system you could be having today. Here's a system we have at Esperanto, 80,000 RISC-V CPUs all running at the same time in one rack. And that's not the maximum you could put. So any of you here who want to start preparing for HPC, who want to do machine learning stuff, buy yourself a rack. Why not, right? One rack can hold 320 of our accelerators, right? You get 1,000 CPUs per accelerator chip. So that's 348,000 RISC-V CPUs in a rack. That's pretty good density here. The performance is pretty good today. 24 petaflops in one rack of int8 precision, which is what a lot of machine learning does. We also have FP16 support and FP32 support, so you can get in the multi-petaflop range. Our current accelerator is focused more for machine learning, So its FP64 capabilities are more limited, mainly to the Maxion processors here. But what we learned in doing this is tricks so we could add FP64 to our next generation, and it wasn't going to blow up the die area. Usually the array multipliers get bigger. We were worried about power and other things. But you know, the ability to innovate with RISC-V has let us build much more interesting systems here. So let me talk about why RISC-V is actually great for machine learning and how do we actually do this in silicon here. So we start with one CPU, right? We care a lot about energy efficiency, so we've started with an in-order CPU, but with some ability to overlap instructions here. But the RISC-V integer pipe is just that little yellow piece there. Really, most of what goes on here is in the vector and tensor unit here that's above that yellow piece there. So there's a 512-bit wide integer vector pipeline, 256 bits wide for floating point. We have done a lot of extensions. This is why we love RISC-V. The vector spec wasn't ready, but we could go ahead and do our own thing for this first generation here, right? And so we've been able to add what we needed to do machine learning well. We then, how do you put 1,000 together? Well, you got to worry about memory system and other things here. So what we do is we put a group of 32 together, and we have groups of 8 CPUs kind of in a cluster, because in VLSI, your wires can only go so far before you start to exceed the clock length. So that worked out pretty well in 7 nanometer. We couple those through a crossbar switch to 4 banks of memory, and then it's coupled to a high-speed network on chip. We also have a high-performance out-of-order processor here. We have 4, we call it ET Maxions. It's a 4-issue out-of-order machine. Most of what we would expect to use this for is for self-hosting. You can boot Linux on this, right? Today, a lot of our accelerator apps actually go into a server with an x86 CPU, but we're prepared to be able to take this over to a 100% RISC-V system in the future here. And then you put all of these things together on a chip, and they're all tied together with a very high-speed NOC. Again, this structurally, the architecture is actually very similar to what Luca talked about this morning here. Very high-speed NOC, but instead of like a 512-bit bus going between there, we actually have like 8 of these 512-bit buses going. So the amount of bandwidth is tremendous here. I think about 8 terabytes per second of bisection bandwidth. You can put 32 gigabytes of memory on the DDR controllers here, and then that lets you put together a full system here. So this is a full system on chip. You can attach flash memory, UARTs, all kinds of other things here. It's really intended to be a full standalone system here. Again, all these slides will be posted online, so I'm not going to spend a lot of time going through the detail here. It's kind of going to give you a flavor of what we've done. And here's a chip with 24 billion transistors. So I think this is the highest performance single chip RISC-V out there. We do it through parallelism. Other people do it by building a big out-of-order core and have fewer cores, and both are valid techniques depending on what your workload is. And we're shipping today. People say, well, what about the power? Well, power is very app dependent here, but you can see as we kind of break down the power and where it goes on the chip, if we look at the one on the far right, just as an example here, where we're doing deep learning recommendation, right? And the heaviest use of that is the RMC3 piece of that. But all 1,000 cores together only taking 11.9 watts. That's not 11.9 watts per CPU. That would be good for one Intel CPU, right? That's 1,000 CPUs only taking 11.9 watts. And you can see kind of how the power goes. We've got good tools for looking at the power on the different nets, adjusting it here. And what we've done is to put our skill in low power technology together with RISC-V, some enhancements for machine learning, and built just an absolute killer chip for machine learning here. You can program this for machine learning just through PyTorch or through Onyx interfaces to anything like TensorFlow or any other standard things. But for this community, we've had a lot of people come and say, well, I want to program down at the RISC-V level. I don't want to be up at the PyTorch level, right? And we can do that. So we have just developed and started to release to early customers a software development kit for general purpose access to the RISC-V, right? So if you wanted to start programming stuff for HPC, get a system, start programming, get your infrastructure there so you'll be ready when the next system hits. I'll tell you about that in a second. So here's what the hardware looks like. Here's one of our newer PCIe cards. On the top without the heatsink, and the bottom with the heatsink. Anybody, do we have any customers here? Anybody got a card? They can hold up a card so people can see what it looks like, okay? So that's our earlier generation card. And then this new card is only half of the height of this card, right? So you can go into low form factor systems here. Okay, so this would be a typical system. We'd have an x86 host CPU, and then you offload all the acceleration workload to the 16 PCIe accelerator cards. So that's 16,000 RISC-Vs you're offloading to right there. We have a variety of configurations you can go into, depending on your needs. And the performance per watt is pretty good. Here we are against an NVIDIA A100, and we're actually better in terms of inferences per second per watt. Okay? Now, they build one giant chip, right, and make it several hundred watts. We take a slightly different approach, which is to say, figure out how much performance you need, and performance will scale up. In machine learning, you can often set up completely independent tasks, so you really get perfect scalability here, right? So here's from 1 to 16 cards, and we're doing about 98% linear improvement in performance here as we go through. So you can pick to be at the same performance as an A100 with 6 cards, or you can go to more performance. Up to you, right? And the cards are small, they're cheap, it's built on RISC-V, so you have a lot of flexibility there. So ChatGPT is all the rage here. So here, well, it's not exactly ChatGPT because that's not open source, but we have the Facebook Meta OPT model running here. And I think maybe this is the first demo I've seen of running a ChatGPT-like thing on RISC-V. So this is running on just one of our chips. We can parallelize it here, but actually what we do is you put in a prompt, and so it's going to put in several sentences here, and then we're going to ask it to summarize what was, just summarize all this in one sentence, what was going on here, right? Another task here is we pointed it to the internet. There was an article about Esperanto in Forbes magazine. So we just, okay, go read that whole article and summarize that, right? So all I'll say is this software is amazing, and it's amazing you can just run it on one fairly low power chip, all being done by RISC-V. So absolutely yes, RISC-V is totally suitable for machine learning here. So just a couple comments on roadmap and what we're doing next here. So again, our vision is to take what we've learned so far about machine learning and combine that with HPC here to build the next system. So our next chip is ingeniously named the ETSoC2, SoC supercomputer on a chip, right? And it's going to be 100% compatible with the new RISC-V vector spec. So we're very happy about the new vector spec. That's going to do a lot of things here. And it's going to have pretty substantial performance. For one low-power chip, I can't pronounce the exact numbers, but I'll just say more than 10 teraflops of double precision in a single chip. And this system is meant to put hundreds or thousands of these chips cooperatively working together in the future here. We'll have the best of the high bandwidth memory. We're working with a great vendor there to give us leading edge access, leading edge semiconductor technology, and ability to put lots of these chips together. So basically you want more memory, just put more chips together and the memory gets aggregated there. So my contention again is that building HPC and machine learning on RISC-V is going to make these systems easier to program. You could use what's called the threaded model of execution, of offloading things and just migrating the thread, as opposed to what's typically called the accelerator model, which is you program an x86, and then you figure out how to program differently for CUDA, right? And then you offload and do that, and things just don't mesh very well. This way we get basically the same programming can work either on the big out-of-order RISC-V cores, or it can work on the small cores. Okay? So I think what we're saying here is our experience has taught us how we can serve both machine learning and HPC requirements together with really very little extra overhead here, right? And our goal is to enable our customers buying our chips to build the top supercomputers in the world here. So in summary, we think RISC-V is not only the best choice, it's really the only logical choice when you think about building great systems for the future here. Okay? Having one instruction set, right, that can scale the range of performance and putting these together in the system is going to be great, and there aren't many alternatives. x86 is just too heavyweight to serve as both the main CPU and the accelerators, and the GPUs are just too hard to program, and they can't really serve as your main CPU, right? Only RISC-V really has the ability to do both things here. And there are a lot of great high-performance out-of-order cores from Ventana, Tenstorrent, Semidynamics. You've seen these here, right? And Esperanto will be providing lightweight cores, and I'm sure other people will as well. Again, we heard from Luca this morning on some very lightweight cores. Anybody can get into this. That's the beauty of RISC-V here. So our view is that RISC-V is now mature enough and ready to start the revolution for future combined machine learning HPC. And I think as you talk to the customers of HPC, they should get excited about this concept as well. So I'll make one final prediction here with what we're doing and what I hear other people are doing, that at least within the next 5 years, a RISC-V based system will win what's called the Green 500 Award. You may know in supercomputers there's a top 500 list. It's the top 500 supercomputers in the world. They then rank those by energy efficiency, and whoever has the best energy efficiency who made it into the top 500 can win the Green 500. So our goal is to make that happen with Esperanto hardware, and we're happy to be challenged by anybody else out there who wants to build other systems there. Let's make this a conversion to RISC-V in the same way that 20 years ago, if you looked at the top 500, there were almost no Linux systems on there. It was all Microsoft, right? Look at the top 500 today, there is only Linux. So it takes a while to get converted over, but I think that's the future of what we can do with RISC-V. Okay? Thanks very much. No. Our intention is, so the question is, do we need an x86 host in there like I showed for our current part? And the answer is no. Our intention is to be able to make these standalone systems in the future. Like 100% RISC-V. With anybody, a lot of big options for out-of-order cores here. I'm not ready to pre-announce which one today, but let me just say, what I love about RISC-V, we have lots of great choices. If I was on ARM, I got like one choice. I go to ARM, that's it, right? And for x86, it's like, oh, well, you can't actually get IP or license anything. You have to buy it from Intel or AMD. There's no choice at all, no flexibility. So RISC-V is the way to go. Okay.
Thanks for the talk. Do you have any example of your system being used to inverse large matrices through blast routing or something like that?
Yeah, so I think the question is about porting HPC software. So there's a lot of work. It's really a community effort there. There's a lot of folks, for example, BSC in particular is helping drive a lot of that. So we've done an assessment, and I'd say, yeah, we're maybe about 90% of the way there. We are behind ARM a little bit. But when people say, oh, RISC-V is 10 years behind ARM, but the answer is yeah, but it's not going to take 10 years to catch up. It'll take maybe a couple of years to catch up. So again, our job at Esperanto has been mainly focused on machine learning. And so what we've done is to make this general purpose SDK available so that those of you who are experts in doing, SGEM or half precision GEM or whatever, you can start programming here, right? And our goal is you should be able to get well into the mid 90% of peak rates here. But it does take some tuning and cleverness in the system here. But we're doing very well in terms of percentage of peak rate on machine learning. Say versus NVIDIA, we have higher peak rates based on RISC-V than they can get out of a CUDA machine. So it's really up to you, the software programmers. Figure out what piece is missing, help generate the last piece, and put it in the open source community. Okay, thanks very much.